Thank you. Okay, so I want to talk a bit about Diviner to follow on the talk that Dave Page gave yesterday and talk a bit about how heterogeneities in the regolith can influence our measurements, specifically focusing on small-scale topography and the slopes and shadowing effects, and also variations in thermophysical properties. So I'm going to talk about surface roughness in rocks specifically and show you two modeling examples. So basically any heterogeneity in the upper part of the regolith, that sort of top tens of centimeters where the diurnal thermal skin depth is, can affect our derived brightness temperatures and cause anisothermality, meaning if there's a variety of temperatures within the field of view, we'll get different brightness temperatures in our different channels. And superposed on top of that is then spectral emissivity. So one of the things we're trying to do is do some thermal diffusion modeling of the regolith and try to disentangle these effects and understand it a bit better. Recently, I've been using this package called COMSOL Multiphysics to do some of this modeling. In the past, we've been writing our own code, some finite difference code, which I showed some results last year. And so we're trying this new package, which seems to be working really well. And our ultimate goal is to go to fairly complex geometries, looking at fractal terrains with various RMS slopes. But initially, right now, we're just looking at simple geometries just to understand the model and understand all the different feedbacks and everything, and how it influences potentially our results. So just a quick overview of the instrument. The main goal of Diviner is to characterize the thermal environment of the moon, also do some bulk silicate mineralogy, understand things like rock abundance and thermal inertia, basic thermophysical properties of the regolith, and then understand areas where you get really cold temperatures, like the polar regions, where you can cold trap volatiles. And this is all done with 9 spectral channels. Two channels, channel 1 and 2 are in the visible wavelength, so we're looking at reflected light off of the surface. Then we have 3 channels centered all around sort of 8 microns that are used to characterize the Chris Johnson feature for doing the mineralogy. And then our 4 longer wavelength channels, our thermal channels, we use for characterizing surface temperatures. So any sort of perturbation to the surface can potentially cause a large variation in surface temperatures. And this is just simply due to the fact that the moon, lacking a substantial atmosphere to buffer surface temperatures, any little shadow or slope tilted towards the sun is going to cause large thermal gradients. And the low thermal inertia of that surface means that you can sustain pretty large thermal gradients over pretty much any length scale, all the way down to tens of centimeters. So on the left here, I'm showing just an example of the polar region. This is the South Pole, where you have low sun angles. You can see the topography really can create quite a complex temperature field. And this variation in temperatures, which here in Diviner is resolved at a kilometer scale, goes all the way down to the smallest scales you can see on the surface, where every little pebble, every little dimple is going to cast a shadow and cause anisothermality in our Diviner data. And so one of the goals here is also to understand what length scale Diviner is going to be sensitive to. What size rock does Diviner consider a rock, for example? So all these different effects will influence heat transport within the regolith. And so we want to kind of understand a little bit better how the regolith transports and stores heat throughout the diurnal cycle. And so just for reference, the Diviner surface footprint is sort of the scale of hundreds of meters. And so we're going to model some features that are smaller. So you're mixing temperatures within the surface footprint. So given a uniform temperature, Diviner all the channels would return the same brightness temperature. But in the general case, that's not going to be true. You're going to get a mixture of temperatures. And so just due to the nonlinearity of the Planck function, you're going to get different temperatures in the different wavelength bands of the channels. So warmer temperatures will increasingly have a proportional influence on the brightness temperature at the shorter wavelength channels. And so we can actually exploit that to say something about the small scale features of the regolith. So for example, this is how we estimate rock abundance. And we have a paper out on that by Josh Banfield, looking at rock abundance. We have a rock abundance map. It's one of our data products archived at PDS. Here's an example then in the data. This is nighttime temperatures in the 4 thermal channels. And so you can see the gradient going from the equator towards the polar. Higher southern latitudes, you can see a latitudinal effect. But then the warm quasi-circular feature is Tycho, which is very rocky, large blocks of rocks that stay warm during the night. And so this is then just a histogram of the temperatures. The thing to note is that if you difference 6 and 9, that the short wavelength channel has higher brightness temperatures at the just due to the warmer temperatures in the scene. You can also see this. Here's another example at the equator in Oceanus Procellarum. So you can see in the daytime temperatures, as the sun angles get low, the temperatures, the shadows become more significant, and you start getting greater anisothermality. So there's a solar incidence angle effect during the daytime temperatures. In the nighttime temperatures, you see also some anisothermality. It actually declines a bit during the night, and this is due to warmer features in the scene, so most likely rocks that stay hot and warm during the night. The rocks have a higher thermal inertia. They can store more sensible heat during the daytime and represent a larger reservoir of heat during the long lunar night to re-radiate back out to space. So you're basically mixing warmer and colder temperatures in the nighttime. And this area that I picked, we actually have a good idea of what it looks like just because this was right near the Surveyor 1 landing site. And so you can see this is an LRO image, and this is roughly the size of the Diviner footprint on the surface. And this is what it looks like from the surface. Here's the Surveyor footprint. It's about 30 centimeters in diameter for reference. So you can see that at every length scale, you're seeing shadows at low sun angles. So every little rock, every little crater, every little pit is going to give you a mixture of temperatures within your field of view, and that's what's giving you that anisothermality. We have a pretty good idea of the sort of bulk vertical profile of the thermophysical properties just due to how the regolith cools through the night. So if you look at this is just showing the diurnal curve at all the equatorial longitudes, and how the regolith cools during the night. The shape of the slope tells us something about the vertical profile of the thermal properties. So we know just from doing the best fit models that the bulk density, we have a very low density, low thermal conductivity layer, very fluffy insulating layer at the surface that grades into a higher density layer at depth. And so this is pretty consistent with what the Apollo found with their heat flow measurements. So again, that top sort of couple centimeters is very low density, sort of this fluffy, almost like a flower layer. We can see this in the Surveyor footpad image by Apollo 12, where the lander actually bounced and left an imprint. You can see the little waffle imprint there is still preserved very well, and it's just a very low density layer. And what that low density layer does is really amplify the maximum minimum temperatures that are experienced by the regolith. And so with COMSOL, we actually were able to reproduce the Salvada model with the minimum maximum temperature. So this gives you an idea of the skin depth as the regolith responds to solar forcing. So now we take this to 3 dimensions, and we can put in heterogeneities and look at how the regolith again responds to solar forcing. And so I'm going to show 2 examples that we've just initially run in COMSOL. One is a bowl-shaped crater at 2 different sizes, 5 centimeter diameter and 10 centimeter diameter, and then also a rock that's hemispherical. Basically fill in the crater then with a high thermal inertia object. So we can look at both topographic effects and then also heterogeneity and thermophysical properties, and see how it affects the Diviner brightness temperatures. So looking initially at the crater, here we can see that this is what I'm doing here is taking just different numbers of craters and putting it in the scene and just differencing that with our homogeneous flat surface. And so you can see the nighttime temperatures generally are going to be warmer, and this is just due to the fact that the cavity is re-radiating infrared, and it's seeing the other walls. And so it stays actually warmer during the night. So the more craters you have, the warmer your nighttime temperatures are. And then once that sun comes up above the horizon in the morning, that low density surface layer heats up really fast, and the craters are being largely shadowed are actually cooler. So your early morning temperatures are actually cooler with more craters. And then during the noontime, they sort of become more of a constant temperature. But then in the afternoon, again, you start to get shadowing effects and slope effects, and so you actually initially get higher temperatures as you get sunward-facing slopes, but then those start to get dominated by the shadows, and the craters then cool off, so you get this sort of little sinusoidal effect here. And then as soon as that sun sets, that surface temperature, that low thermal inertia regolith just cools off right away, and those craters stay a little bit warmer, and so you get this spike in temperatures. Okay, so this is now looking at channel 4 minus channel 7 and channel 6 minus channel 8. So this is showing the anisothermality that results then, and the red is the 5 centimeter craters, and then just doubling the radius on those to 10 centimeter diameters. And then just as you increase the abundance of these craters, you can see the anisothermality goes up. So in the daytime, you're seeing the slope effects as the sun angle gets low and the shadows get large. You increase the anisothermality, which is what we see in the data. And again, the nighttime temperatures, you see anisothermality again, just due to the fact that the crater walls are radiating heat within that cavity and keeping the craters warm. Okay, so last example, the flat rock. Again, the rock having a higher thermal inertia stays warm during the night. So it gives you see it right there. And so you get warm temperatures during the nighttime. Again, it's sort of similar to the crater in some ways. Again, the response of the rock is basically just slower to changes in illumination conditions than the surrounding regolith. I don't really have time to go too much into it since I'm out of time, but the main point here is, again, this is just nighttime temperatures. And again, you can see that as the rocks cool more slowly, you get anisothermality at nighttime. But there also does appear to be a scale dependence. So again, the larger the rock, the larger that signal. And so we want to kind of characterize what length scales we're going to be sensitive to. And again, this is how we model our rock abundance, just mixing different ratios of rock and regolith. And since I'm out of time, I'll go ahead and wrap up. But the point is that there's extreme variability in surface temperatures at pretty much all length scales. And so we want to try to exploit diviners, the anisothermality in the diviner channels, to really kind of get at some of the thermophysical properties and all these different effects, and try to understand diviner sensitivity to all these different effects. Thanks.
We have time for a question. There's a question.
So think about micron scale. Yeah. Right. And that's something we can look at and try and understand better, but certainly that it'll. Yeah, so I mean the dust is very insulating. So anywhere where you've got more dust versus less, it should actually have an effect. And that's something, again, we'll try and look at some more as we start to understand this model a little better and start playing around with it more. I've only been using the model for a couple of weeks, so